And I'm free, free falling. You may have heard that song before. Uh, it's an expression we use sometimes. What does it mean in physics, though? This video is going to talk about the way a physics person would view the concept of free fall. It might have a little bit of a connection to the feeling of free fall. I'm free falling. If you're free falling like in that song, you seem to have lost control. Something else is in control. Gravity. So we're going to be talking about this in the video. We're going to go over what is free fall exactly, when do I use this concept in physics, and also I have a couple of example problems where we're using the concept to solve a problem, a kinematics problem. Here is a unit outline for what we're doing with kinematics, and this is our last topic. So you get to that part of the homework. You basically need to understand what is free fall and be able to solve certain problems using the concept of free fall. So free fall is pretty much exactly what it sounds like. I'm falling freely, but why am I falling if I'm falling freely? It's because of gravity. So here is a video I made which illustrates a famous idea. So let's watch the video. And we can also, I think, go back and slow it down even more. So you can try this experiment at home. What do I have here? I have two objects that are very different in size and mass and weight. They're both made of steel, but the one on the left is much larger, much heavier, and yet they fall together in link. Seems like they're synchronized every time. Every place in this video we can see they're in the same place as they fall. So this is a famous idea which you may have heard of before. The credit for this is usually attributed to Galileo, and you might have heard of that before, that Galileo came up with this idea supposedly by dropping objects off of the Leaning Tower of Pisa. Now, whether that really happened or not is, I think, debatable. Galileo actually did experiments with ramps and came to the same conclusion. Here's a different experiment. You might have thought, oh, well, maybe it's just those spheres. Maybe steel objects fall at the same rate. So in this one, I've got some very different objects. In one hand, I have a steel bolt, which came out of a garage door of all things. And then in the other hand, I have a small figure made of rubber, which is Gumby. Let's watch. Once again, we see synchronization. Who is this guy Gumby? Well, if you never heard of Gumby, look him up. It's just a little toy I use for certain physics demos. Gumby is much lighter than this steel rod, and yet those objects are also falling synchronized. So this idea is what we call free fall. So what is free fall? It's this concept that objects fall in the same manner if they are under the sole influence of gravity. And it's interesting that smaller objects can have the same acceleration as larger objects. We would think a larger object or a heavier object might fall faster, and yet if we watch carefully in the videos, we see that doesn't appear to be the case. It is useful to know that if we measure the acceleration of such an object, we find that it's going to be 9.8 meters per second downward. And that means that as the object is falling, its velocity is increasing, or its speed is increasing 9.8 meters per second every second. That's about 10, which is kind of a rough way to say it. Every second that goes by, if you're falling, you're moving 10 meters per second faster. So if you fall out of a plane, I hope that never happens to you, but if you did, after a second you would be going 10 meters per second. After another second you would be going 20 meters per second. After another second goes by, you would be going another 10 meters per second faster, or 30 meters per second, and so on. In rough terms, again, roughly 10 meters per second squared. 9.80 is a mean value measured in lots of places around the Earth, and it's an interesting concept. Now, one of the key things to point out here is that this is true. There is a catch. So I hope that you noticed in the statement here that we have this little expression, under the sole influence. So that's kind of your catch, is that for this strictly speaking to be true, it needs to be only gravity affecting the object. Now, if I drop a lightweight object like a piece of paper or a feather or something, then we can think about that. It's obviously not going to keep up with the objects in my video, but it's because something other than gravity is affecting it. So it's not freely falling, not as free as if when gravity is the only thing. A lot of times we ignore the effect of air resistance. Air resistance would affect anything that's falling in our everyday lives. So in my videos, there obviously was air in the room when I made those videos, and those objects would have been influenced a little bit by the air in the room, and that's called air resistance. That would impede their fall a little bit, and as you might imagine, that would cause their acceleration to perhaps be a little less than the value shown here, 9.80 meters per second squared. We'll talk more about air resistance in just a moment. The other thing that we might note here is this says mean value, which is kind of interesting. That implies something. And then we also have this near the surface of the Earth. So mean implies that it varies a little bit. And we also have this stipulation that we need to be near the surface of the Earth for this to be a valid number or quantity to use. I have an interesting slide here. Let's look at it. Which shows the value of G in various places. So from various places around the world and in the United States, we can see the value of G as determined, very precisely by the right instrumentation and the right measurements. Here in Knoxville, we've got a couple of values shown there, TYS and UT. That's at the airport and at the University of Tennessee. And it's slightly different. That's kind of fun to think about. If you drop an object at the airport, it's going to fall maybe a tiny bit different than it would fall if you drop the object at the University of Tennessee. Why would that be? Well, UT is on the banks of the Tennessee River, and the airport is a greater elevation than that. Notice the value at the airport, TYS, is slightly less than the value at UT, which is on the river, a lower elevation. I don't think it would surprise you to think or realize or consider the idea that gravity is going to be less the further away from the Earth I go. So if I go to a greater elevation, that's going to cause gravity to be weaker, and that causes an object to fall just a little bit slower. Mexico City is actually fairly high elevation. It's not the only thing, so you might find some exceptions to that in the example shown here. Denver has also got a great elevation, and yet its value of G is actually pretty close to what it is in Knoxville. So, but just realize for now, we'll worry more about gravity later, but for now, just realize that gravity has a value, and look at all of these numbers. If you round them to 3 significant digits, in most locations, it would be very close to 9.80. So that's a convenient number, and that's the most commonly used value for the acceleration of gravity, 9.80. Now back to the concept of air resistance. I'm just going to go over a couple of things here. Later in the year, we'll talk more about air resistance, but we want to use that number, 9.8 meters per second squared, when we can. It's nice. It's a very useful number, as you'll see in just a minute. It's a useful value. So we want to use it if we can safely assume that air resistance is not going to have a significant effect. So when does air resistance have a significant effect? Air resistance is greater if, well, maybe you can think of some things. Why would an object get more air resistance? Well, one thing would be simply the size of the object. If it's falling through the air and it's bigger, it hits more air. That might sound funny to say it like that, but an object moving through the air is running into air molecules that are just kind of floating there. So if you have a greater size, you're going to run into more air molecules, and that's going to increase the amount of air resistance. There is a factor that's kind of complicated, the aerodynamic shape of the object. You might have heard about this with automobiles. Over the years, they became more and more streamlined and smooth curves, and that helps them to kind of slice through the air a little bit better. And then finally, the last one on my list is speed through the air. If you're moving through the air faster, then the air has a greater effect on you. So here's a simple thing that you could think about. Imagine driving in a car that has a moonroof, and the moonroof is open, and you're going 10 miles per hour. You stick your hand out the moonroof, and you can feel the air. But now, suppose the speed of your car increases, and you're going 100 miles per hour, and you stick your hand out the moonroof. Can you imagine feeling that force much greater, pushing the air, pushing on your hand much greater if your car was going 100 miles per hour? Well, yeah, I mean, if you hit the air molecules at a higher speed, or vice versa, the air molecules are hitting your hand at a greater speed, then there's going to be a greater effect. And that happens with falling objects. An object accelerates. If it accelerates enough, maybe it ends up going really fast through the air, and then air resistance is having more of an effect. We'll talk more about that later in the year also. But we could kind of summarize here and say, okay, when can I use the value of 9.8 meters per second squared? Well, the slower and denser the object, the less is going to be the relative effect of the air resistance compared to what gravity is doing. The objects in my video were fairly slow moving and fairly dense. And therefore they fell at an acceleration very close to 9.8 and very close to one another. They had essentially the same motion as best we could tell watching the slow motion videos. Here is an interesting comparison, one more video that I made, and this is showing an object that you might expect to be affected by the air, a bill, a $20 bill, and a washer. A metal washer. But even the $20 bill, if you look at what happened in this video, let's see if I can. Well, I'm having trouble here. There we go. Even the $20 bill is falling pretty much like the washer, maybe a little bit slower. And that might be because of air resistance. Hopefully this is convincing that even something like that might surprise you. When you first drop it, it's moving fairly slow. And also the way I'm holding it, it's kind of slicing through the air. If it gets turned sideways, it's going to hit a lot more air as it falls. All right. Now, the last part of this video has some example problems. So I've been teaching physics for a while, and this is one of my favorite problems to work as a first example of a free fall problem. So I'm kind of a fan of the New York Times, and once I read this article in the New York Times about cats surviving falls out of apartment windows in New York City. And the article said that cats could survive a fall of up to 12 stories high or 12 floors high. So fall out of a 12th floor apartment window and survive. So I thought, oh, that's an interesting story. I wonder, what is the impact speed of a cat that has fallen 12 floors? How fast is a cat moving if it falls that far? Well, that would be about 40 meters, say, and we're going to estimate what we would call in physics the impact speed. So I have a diagram, and diagrams are always helpful. Pretty simple diagram here. I'm just imagining, okay, here's my cat, and my cat's up here, and it fell out of a window. Well, it's falling 12 floors according to the article. And then how do I solve this problem? Notice there isn't much given here. All we have to work with is, okay, it fell a certain distance. So how am I supposed to solve this problem if I don't have much information? Step one is to recognize, hey, a cat is an object falling, and a cat is in free fall, and a cat is reasonably dense and not that fast moving, at least not at the start. We're going to make a reasonable assumption that the cat is in free fall, and in New York City, as in lots of places, the acceleration would be 9.80 meters per second squared downward. So that's not a given value in this problem, but it's one that you need to take to be true, assume to be true to solve this problem. So that's something you're expected to understand, is that, okay, if I read this problem and I know the cat's in free fall, I recognize, okay, the main thing affecting this cat is gravity, then you're not going to be told, hey, the acceleration is 9.8 meters per second squared. You should know that as a physics student. But once I have that bit of information written down and in my head, I can use that, then the rest of this problem is basically just another kinematics problem, similar to ones that you have already worked. We're looking for the velocity at the end of this motion, impact speed, and we're going to be trying to use our formulas. We're going to make a reasonable assumption. Physics problems often have kind of reading between the lines. So this is interesting. So I'm trying to find the velocity after I fall that distance, and then what is my velocity at the beginning of that? Well, if we're going to make a reasonable assumption that the cat started at rest in the apartment window. What else can we do? I mean, we need to know that. We're assuming the cat was not thrown out of the window. We're also kind of assuming the cat didn't jump out of the window, although the cat simply just falling out of the window seems a little unlikely. There's kind of nothing else we can do. It would affect the answer if the cat did not start at rest. So we're going to assume it started at rest. And then we're looking for the final velocity. And we're going to use our same formulas. The whole time it should be accelerating at 9.8 meters per second squared. That means formulas that we use for constant acceleration apply to a freely falling object. And that part is something you've already seen. The initial velocity is at the beginning of this motion, so that's 0. And I can mark those terms out of my equation. So VI is 0 here, VIT is equal to 0 there. And then we're looking for VF. Now, something might occur to you that, wait a minute, what is the final velocity of a cat that has fallen onto pavement? Well, ultimately, the velocity is going to be 0, but that's not what we're looking for. Impact speed would be the velocity right before the cat hits. The cat's definitely going to stop moving. However, our value that we're using, 9.8, here's a subtle but important point to be made. This value we're using, 9.8 meters per second squared, is when gravity is the only thing affecting the cat. The cat is under the sole influence of gravity up until the point right before it hits. As soon as it touches at all, it is under the influence of something else. Pavement. And our value for acceleration does not include the effect of pavement. So I'm trying to say this in a kind of lighthearted way. By the way, I might point out I have nothing against cats. I'm not advocating cruelty to cats. And the story said they survived. So it's just an interesting problem to solve, hopefully. Anyway, we're looking for the final velocity in the sense that the final velocity in the free fall part of that motion. And then we should be able to finish the problem. So how do I solve this problem? I'm going to use the displacement 40 meters, and realize that that should be equal to 1/2 AT squared. And then I know the value of D is 40, and I know the value of A. So I can rearrange that, do a little algebra, and solve for T. And then once I have the value of T, I can calculate it. And here I get this amount of time, 2.86 seconds. And then if I'm accelerating for 2.86 seconds, gaining speed 9.8 meters per second, I'm going to get my final velocity by using that information, acceleration times time. And that gives me this velocity, final velocity 28, although the problem asked for speed. So speed is a scalar, and I don't have to give a direction for that. I really should not give a direction. I should just give my answer as 28 meters per second and round off because of the significant digits. So here's our answer to the question: what is the impact speed of the cat if it falls that distance? 28 meters per second. That's pretty fast. That's like 60-something miles per hour. Yikes. Actually, if you think carefully about it, we're ignoring the effect of air resistance. Air, if anything, would cause the cat to not accelerate as great as this. In reality, what would happen, the cat would start out accelerating at 9.8, but eventually it's moving through the air fast enough that the air would help to lessen the effect of gravity, you might say. So this number would represent the fastest that it could be moving. In reality, would probably be moving somewhat less. Without more information, we wouldn't have any way to determine how much less. So this would be a reasonable way to solve the problem and get an estimate. Notice it said estimate. And this would be our value, our answer. Okay. So I hope this problem makes sense to you. That's a classic problem. Object falls, find the speed after it falls a certain distance. Now there is a different use for gravity that I want you to see, and it's illustrated in a different video that I made. So watch this video. Notice what's happening in this video. We've got our objects. This time were not dropped, but they were launched upward. I threw them upward. And they moved upward together. They reached their highest point together. And then they came down together. So that's interesting to see that motion and to realize that gravity is affecting those objects as they're rising and as they are falling. And the number that we have, 9.8 meters per second squared, applies to the objects as they are rising. Like the effect of gravity in terms of acceleration is the same. If the objects are moving upward but their speed is decreasing, they're accelerating downward. And that's the same acceleration they have when they fall down. So that's a little factoid that you need to be comfortable with, that the acceleration of gravity works as long as gravity is the only force. I mean, think about it. These objects, after I let go of them, only gravity is causing them to slow down and fall back down. So gravity is the sole factor. We're ignoring air resistance again. And the acceleration, 9.8 meters per second squared down, is going on the whole time. As soon as those objects leave my hand until they come back, the acceleration is 9.8. So right about here, both objects are accelerating downward at 9.8 meters per second squared. Same thing here, same thing here, same thing here. When they reach the highest point, they're accelerating downward at 9.8, and then they start to pick up speed, and they're still accelerating at 9.8. The entire time, they're accelerating downward at 9.8 meters per second squared. I have a classic problem here. You'll see this in pretty much every physics book, a problem like this, where an object is launched upward and then you're asked to figure out, well, how high does it go? So suppose you're watching a baseball game. Sometimes in a baseball game, the batter might hit the ball incorrectly and the ball might shoot straight up pretty much. And then the catcher might just stand up and catch the ball. So here's this problem. Suppose the baseball has an initial velocity straight up, 20 meters per second. What is the maximum height and what is the total time for the ball to return to its initial position? Like, how long is it in the air? That's kind of a fun thing to figure out also. So let's look at our solution for this one. As usual, I have here a diagram. So I've shown the ball over here starts at some velocity upward. It's going to rise for a while, but then I just kind of moved it over a little bit so I could show it. It's going to fall back down, obviously. We're looking for how high did it go, and then also total time, like total time to get back to where it started. So that's our problem here. So how are we going to do that? We're going to once again realize, hey, this wasn't given, but it's a reasonable assumption. A baseball is a reasonably dense object, not affected a whole lot by air resistance, so we would assume it's going to have a downward acceleration, 9.8 meters per second squared. And then I want to start thinking about the problem. I have what's pretty obviously the initial velocity, 20 meters per second. And then I'm looking for the maximum height. So that high point is an important point. We saw it in the video. The object is rising and its speed is decreasing. But then after that, its speed is increasing. There is a point, one point where it stops rising, starts falling, where the velocity is, I hope you know what I'm getting ready to say. The velocity at the highest point would be 0, and that's going to allow us to solve this problem. I'm going to use the same formulas, but I could say to myself, well, I know the velocity at the highest point should be 0. So I've added that over here. In my diagram, velocity is 0 at that highest point. And then I can use the formulas. I have the initial velocity, and if I know that velocity is 0, I can set the final velocity equal to 0, the initial velocity equal to 20, and solve for t. This is not the answer to the question total time in the air, but this is the time for the ball to reach the highest point. Notice I put these little dashed lines here kind of showing that we're focusing on only one part of that motion. And sometimes we do this in physics. We might break it down and say, well, let's forget about the falling back down part and just focus on the rising part. The final velocity of that part is 0. And then I can use that to figure out the time for the ball to rise to the highest point. And that's 20 divided by 9.8. Roughly it's going 20. It slows down 10 every second. So it goes from 20 to 10 to 0 in about 2 seconds. We can get the exact amount by dividing 20 by 9.8. But then I can plug into my other formula, and that's going to be my maximum height relative to where it started. This formula is always displacement. So if I do that calculation, I'm going to end up with the displacement relative to where it started. So presumably it was hit by a bat. So it's going to be that high above the bat or where it started. Notice there is a very important negative sign right here. My object is moving upward. That's velocity positive, but it's accelerating downward. That's acceleration, a negative value. If you leave out that negative, you get a very different answer, a very wrong answer of about 60 meters. So it's going to be way off. So don't overlook an important negative in this type of problem where I've got essentially a deceleration, at least on the way up. So this is our completed solution for the first part of the problem, which is find the maximum height. So I hope that makes sense to you. And then we're going to also answer the total time. Now, you might have kind of a guess on this one. And in fact, having taught this class a lot for a long time, I know students would often just kind of reason out, well, the total time, well, if it takes 2 seconds to go up, it's going to take 2 seconds to come back down. So wouldn't I just double that number? I wrote that over here as just kind of a guess in a way. Maybe it makes sense to you, but if I doubled that amount of time, 2.04, the time to go up, would that give me the total time, which would include going up and coming back down? Well, we don't have to guess. There are actually a couple of ways you could show that, yes, that's going to be correct. So let me share those with you. First of all, one thing I could do is focus on what happens when it comes back down. So I have here a calculation, the time for it to fall back down. And once again, I'm showing with these dashed lines here, and I'll also use my little pointer. Time to fall down, if the velocity is 0 if I kind of start over. Let's say that now this is my initial velocity, the highest point, and I want to know how much time will it take to fall down. Forget about the rising, so now we're just focusing on the falling. That's a totally valid thing to do. I can analyze anything I want with these formulas as long as I know I've got a constant acceleration. In this case, I know it would be 9.8. And you know, if you think about it, the ball falling back down is the cat problem all over again. It's the same problem. So the ball starts at 0 when it's at the highest point, and then it simply falls now a known distance, right? We know that that distance would be 20.4 because we already calculated that. And then I'm just using distance equals 1/2 AT squared. So like the last problem, I didn't write out as much detail this time, but like the last problem, I could get the time based on distance equals 1/2 AT squared and use the distance that we now know, 20.4 meters. Sure enough, it's the same amount of time we had here, 2.041 seconds. And that means that, yes, the total time in the air would be double 2.041. 2.041 going up, 2.041 coming down. There is another way that you can show this, and I want you to pay attention to this, even though you might say, well, why do I need to know another way? This other way has some important aspects to it that I think should be helpful. So here's a different way you could figure this out. Set the displacement equal to 0. And if we do that, we're considering something else. So far we did an analysis of what happens when it rises, and then we did an analysis what happens when it falls. But I can also analyze the entire trip if I want to. This analysis is the whole thing. So notice I've circled the whole thing, and if you think about the whole thing, like the entire trip, I started out with initial velocity 20. The acceleration the whole way is downward, 9.8 meters per second squared. And if I come back to where I started, this is kind of the catch for this part, which is kind of weird. If I come back to where I started, my displacement is 0. Why? Because my net change in position is 0. I'm back at where I started. Overall, displacement is just from where you start to where you end. Well, if I come back to where I started, that's 0. And it might surprise you that that gives me a correct result as also a valid solution. Now, this is also an interesting thing to look at. I have t and t squared. This formula is a quadratic type of formula, and some of the things you learn in algebra are important. Sometimes in physics, how do you solve for t if you have a t squared and a t? Usually one of two options. One option would be use the quadratic formula, which is fine, negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Or factor. Yes, factor. So this actually is pretty easy to factor. That's what I decided to do here. You could factor out a t, and if I factor out a t, then I see, okay, I've got t times quantity 20 minus 4.9 t. And then we have this rule, okay, well, one of those two factors has to equal 0 if the product is 0. And that means either t is 0 or the quantity 20 minus 4.9 t is 0. And then I can solve for t that way. 20 would be equivalent to 4.9t, and then I can get the time, and this would be the total time this time, by dividing 20 by 4.9. And that gives me the same answer, 4.08 seconds for the total time. Notice here I can see it's going to be exactly twice what we had before. Over here we divided 20 by 9.8, and then in this alternate solution I'm dividing 20 by 4.9, half of 9.8, so I get an answer that's twice as great. So here is our completed solution for our baseball problem, and I hope that you understand how we got these answers, and I hope that you're feeling like you understand what is free fall and the way it's a useful concept in physics.